Yeah, so we switch gears a little bit, and it kind of comes back to one of the questions: why do we do all of this? And as I said, a lot of my colleagues, this is what they do for a living. They study the nuclear structure, and just from a basic research point of view, try to understand all this shell evolution, discovery of new isotopes, discovery of new elements, and all of that is a field on its own. It's a big fraction of this low energy community. I would say maybe half of the community is doing that. I am interested personally in a big fraction of the community is doing, the application side of things. And one of the big applications is in astrophysics, trying to understand how the elements we see around us are produced in stars, how just to explain the different astrophysical phenomena. And so all of that is driven by nuclear processes. And so that's what I'll try to do in the next 40 minutes or so, is to give you a taste of the many different processes. Again, we don't have to dive into too much detail, but I want to give you a flavor of what's going on. Okay, so this is kind of how I see the field of nuclear astrophysics. Is it okay if I walk around, or do I have to stay here?
I think so. I mean, if somebody from Zoom cannot hear, I let you know.
Okay, yeah, just let me know. It's just
text me.
I want to be a little bit further away. Okay, so this is how I see the field of nuclear astrophysics. So it's always, there's some kind of observable that we're trying to explain. And these observables are coming from many different sources in the universe. It can be something like this, which is the abundances of different elements we see in the solar system. It can be from telescopes in space or on Earth, looking at distant stars. It can be gravitational waves like what we had recently. Again, different light curves from different stars. And it can also be from meteorites, the meteorite itself, but there's also little grains inside the meteorite that can have different sources. They're called pre-solar grains, and they can have characteristics that have nothing to do with the solar system, and they came from events that were done before the solar system was created, and they just carry that signature. So this is a whole field of trying to get unique signatures from different stars. Yes?
Do you have an example of what that, like signatures of other?
Yeah, so for example, you look at different elements, and I'll show some, but you look at different elements and you say, okay, in the solar system, we see that there's more, I don't know, iron and there's less rhodium. But then you look at some of these pre-solar grains and you can have the opposite. Or the advantage, okay, then this is a big point here, is that anything we have from stellar observations, these are all elemental abundances. We cannot see isotopes. All the isotopes will give the same signature in the spectral lines. But if we have a meteorite and anything we have within the solar system, then we can analyze, we can put them in a mass spectrometer, and we can see isotopes. So this is a huge advantage. And so this is probably the biggest thing you get from these pre-solar grains is you see isotope differences that do not follow the patterns that we see within the solar system. So again, you see, okay, this has a different origin. Maybe there was a nova explosion. Maybe there was a supernova. Maybe there's something. Okay, so you have all of these observables, and there's many, many more. And we're trying to figure out what is going on, what is causing, what is creating these kind of observables. So you have to create models. And these models have as an input the astrophysical environment, the conditions, the temperature, the density, everything that's going on in the star. And then, of course, you have all the nuclear physics that's going on in the star itself. What kind of nuclei are there? How do they interact with each other? What are the probabilities? How much energy is released from these reactions? How much energy is released from their decay? So these are all things that we need to put accurately into the model if we ever hope to understand all of these observables. So me personally, I'm sitting on this side, so the experimental nuclear physics. There's there's theoretical nuclear physics. So there's a whole lot of things that we cannot measure experimentally, and that's we have to rely on theory to provide that input. And again, all of this goes into the astrophysical model that then compares to the observers. So that's the story. That's how the field works. So this is a characteristic. This is the solar system abundance distribution. And I can probably spend the next 40 minutes just talking about this plot, which I'm not going to do, but there's a lot going on here. So for example, I mentioned the binding energy and the fusion reactions going all the way to iron. This is immediately, there's a fingerprint of that in the abundance system, solar system abundances. And that is because right around iron, right around here, there's a peak in the abundance system. Kind of lighter elements are easier to make. That's why you have more and more and more, but it keeps going down. But right around iron, there's a peak. And that's exactly because of that stronger binding of iron. Past iron, it's very hard to do any kind of fusion reactions, or it's impossible. So there are different ways to make the heavier elements, and that's why all these abundances are going down. This is a logarithmic scale, huge. From here to here is 5 orders of magnitude. So these are huge changes. And so anything heavy, there's not very much produced just because it's hard. If I go back to the lighter elements, there's a whole group of elements here, lithium, beryllium, and so on, that are very hard to produce. There's a lot of hydrogen and helium just came out of the Big Bang, and everything else is made in stars. And there's again ups and downs here that have to do mostly with nuclear physics properties, the pairing effect that we talked about. The peaks here, I'll show them in a little bit, but they all correspond to a magic number in nuclear physics. So there's so many features on this plot that come from nuclear structure effects that it's just a one-to-one correlation. It shows you again that the better we know the nuclear physics, our nuclear structure, the better we can understand how this works. So it's just amazing to think that we're sitting in our lab studying nuclei and how that shell magic numbers evolve apart from stability, which just kind of sounds like, okay, if you're interested in that, great, but if not, then why are we doing this? But then that would be the cause for a peak in the abundances we see in the solar system, all the elements that we are made of. So it's just mind-blowing if you think about these connections. Okay, so another important thing to point out here is that anything we see in these abundances and any abundances we see in stars, it's not a result of one astrophysical event or one process. It's many. So there can be something, a star is born from a cloud of gas and dust. It evolves, and then let's say whatever it explodes or it ejects material into the interstellar medium. So whatever was created during this phase, it's emitted back into the interstellar medium. So then the next generation of stars, which will be formed by the same cloud of gas, will now be a little bit more enriched in heavier elements. And then the next generation of stars has more. Again, it keeps going like this. So every generation of stars produces a little bit more. And the first one could have done one thing, and then the next one could have done something very different. So after a few rounds of this, you just have kind of a mixture of all of the astrophysical processes. That's why when astronomers try to identify individual processes, they have to go to very old stars. We call them metal poor stars. So it's stars that don't have a lot of these heavier elements, because those maybe they only have one or two of these cycles. And then you can identify features of individual processes. So this is an important thing to know, that what we have here, there was this stellar evolution happening hundreds of times. Okay, so from the nuclear physics point of view, well, it's both nuclear physics and stellar evolution linked together. The way things work is that a cloud comes together from gravitational forces. And then as the temperature in the center starts to increase, the majority of that cloud is hydrogen. No matter how much it was enriched, it's still mostly hydrogen. So as the temperature goes up, then you will start to have that hydrogen, reactions of hydrogen. So proton plus proton. If you fuse proton plus proton, you don't really get anything. You make helium-2, which is unbound, and it immediately breaks into proton and proton, so you cannot really do anything. I'll get back to what exactly is going on from the nuclear reactions. But you do have production of energy from the fusion of hydrogen, and this balances the star. So imagine the star is getting smaller and smaller from the gravitational forces, and now there's an energy in the center that balances this. And this just stays like that for millions and billions of years. This is what our sun is doing right now. and it will just continue to do it for about 10 billion years. At some point, it runs out of fuel in the center, and this process produces helium. The fusion of hydrogen produces helium. So once it runs out of fuel in the center, and now it has helium, the helium needs a higher temperature to fuse. It cannot do it at the same temperature that the hydrogen was doing it. So because the temperature is whatever it is, and now you have only helium that cannot fuse, then there's nothing to balance the gravitational collapse of the star. So it keeps pushing to go in until the temperature again in the core raises, and then helium starts to fuse. And again, it balances the star. It stays like that for a while until it runs out of fuel. And then the next cycle starts. It will go collapse a little bit more, increase the temperature, and a new type of nuclear reaction is ignited. And it just keeps going like that. And all of this whole process keeps going. It keeps going through and creates this kind of shells inside the star. Some of the stars will stop this evolution process very early, or some will not go very high, will never create an iron in the center. It will stop probably around carbon and oxygen. But if it's a heavier star, it can evolve all the way to an iron core, as we say. And then there's all of these shells that each has a different temperature and a different composition, and they all burn fuel at different rates, let's say. And this is what a very massive star looks like, with hydrogen, helium, and so on, all the way to an iron core. Now you saw the binding energy picture. Iron is the most bound, and then anything above iron we cannot have fusion reactions to produce more energy in the star. So once the star produces an iron core, then there's no reaction that will produce again energy to balance that gravitational collapse. So the whole star collapses, and that's where it bounces back, and that's where the supernova explosion happens. And so during this supernova explosion is where you can have other processes now take place, and not just through fusion reactions, but a lot of other things that will come into play. So this is what we call the fusion or the burning stages of the star, and they will produce elements all the way to iron. And then above that, there's a lot more going on that I'll come back in a second. Okay, direct evidence for nucleosynthesis in stars. How do we even know that all of this is happening? Well, the first observation was in the 1950s, where there was an astronomer, Paul Merrill, who was doing his observations. And at the time, people didn't really know what was fueling the stars. They were starting to have some suspicion about nuclear reactions. It was right at the same time that the field of nuclear physics was, we were trying to understand a little bit better what's going on. So there was some suspicion about nuclear reactions, but it could have been that all of the elements were made during the Big Bang, and that's it, that the stars are not really making anything else. So Paul Merrill was doing his observations, and he saw something weird. He saw lines here that correspond to the element technetium. Now, technetium is an artificial element. There's no stable isotope of technetium. The longest lived isotope of technetium lives for 4 million years. So anything that was produced during the Big Bang, any technetium that was produced during the Big Bang should have decayed away a long time ago. So we shouldn't be seeing any technetium lines anywhere. So that was the first observation. It's like, okay, if there's technetium there, it means that the star is probably making that technetium. So that was the first, I consider this the birth of the field of stellar nucleosynthesis. It was the first evidence that, okay, there's heavy elements produced in the sun. There's a lot more. Neutrinos from the sun is another one that, through all of these different reactions that are happening or decays, there's neutrinos coming out. I'll show some of the reactions later. So just seeing neutrinos coming out of the sun all the time is another indication there's active reactions going on. And there's a lot more. I'll show a last example. This is aluminum-26. So aluminum-26 has almost a million year half-life. And we have gamma ray telescopes in space. Those gamma rays don't make it on Earth, they stop in the Earth's atmosphere, but with telescopes in space, you can measure those gamma rays, and they're coming out of the decay of aluminum-26. So again, a million years, less than a million years, it means that aluminum-26 must be produced kind of as we speak for galactic timescales. This is fresh, this is very new. So if we see that signal of aluminum-26 decay across the galaxy, and it's mainly coming from the center of the galaxy, it means that there was some nucleosynthesis events that produced aluminum in the last million years or so. So this is really active. So these are some examples, and there's more. Okay, so let's dive into a little bit of the nuclear physics of things. How does this work? Let's assume just a very simplistic case. Here's my chart of nuclei. Let's assume an environment with just hydrogen. So the first thing that could happen is that the two protons will fuse together to make helium-2. And if I go to my chart, helium-2 would be here, but it's unbound. So immediately those two protons break into pieces. The way that nature figured out how to actually progress is during the fusion of the two protons, there's a weak interaction going on, and one of the protons is converted into a neutron. I'm sure talking about the higher energies and so on, quarks and whatnot, there's a deeper level that you can think about this, but to a higher level, neutrons and protons, this is what's happening. There's a positron coming out and a neutrino. So we talked about the neutrinos coming out from the sun. Now, this is a critical thing. It's another mind-blowing thing for me, is if the previous reaction was possible, we would not be here to talk about it, because there's so much hydrogen. So as soon as the temperature is high enough for hydrogen, the two protons to fuse together, then all of them would just fuse, and our sun would stop burning a very long time ago. So all of the fuel would fuse very quickly, would be consumed very quickly. But because this reaction is so hard to do, our sun will continue to do this reaction for 10 billion years. So this is one of those. There's many of those, but there's one of those reactions that kind of, the reason we're here is because it's hard. It's a hard reaction. Anyway, the rest I will just continue quickly. There's once you make the deuterium, you can grab another proton, make helium-3 and keep going and make helium-4. So I'm not going to stay at every single reaction, just giving you the big picture. There's nuclear reactions happening that can bring you from, in this case, from hydrogen to helium, and we just keep going like this. So I think I have examples. So the previous one was called a PP chain. There's a variation of the PP chain that looks more like this. So again, fusion of hydrogen and helium, but it involves a little bit heavier elements. Going heavier, going nitrogen, oxygen. Again, this is just to get an idea how things get more and more complicated the heavier you go, because they involve a lot more nuclei. And you go over here, we're not even at iron yet, we're not even at titanium, and see how complex this reaction network is, and it just gets more complex as we go. But this is what we have to do. So if you want to understand the element synthesis or the isotope synthesis in stars, you need to know exactly every single one of these reactions, how it works, what it emits, what particles, what energy, what is the probability, if you're going to understand the flow and how much of each of these elements you're making. So we put it all together again on the nuclear chart. And so the stellar burning that I talked about, all the reactions on the previous slide, would all fall into this category. These are mostly fusion type reactions. We do have an environment with a lot of hydrogen and a lot of helium. So the easiest thing to do is capture one of those protons or capture one of those alpha particles and have those kind of reactions. And this is the standard thing that's happening all the way up to iron. Now we get to iron, and iron is very bound. There's a large Coulomb barrier that doesn't allow more protons or more alphas to get captured. So if that happens, we cannot make heavier elements through those type of reactions. There's no energy released to help with the balance of the star. There's a lot of problems around iron. So nature, the way nature figured out how to move forward is through neutrons, because they are neutral and they don't care about the Coulomb barrier. And so this is how everything else progresses from this point on. So there's different neutron-induced processes that I'll cover in the next few slides. S is for slow neutron capture. R is for rapid neutron capture. And you see the slow neutron capture process goes right around the stable isotopes. The rapid one has so many neutrons in the environment, it can push very quickly into very neutron-rich isotopes. So going back to the discovery and so on, the arc process takes place in the region of the chart of nuclei that we haven't reached experimentally yet, that gray region that you were asking about earlier. So that's one of the reasons that we're trying to push into discovering new isotopes, is to understand how some of these astrophysical processes work, especially the arc process, because it makes about half of the isotopes of heavy elements. So if we don't understand how this works, then we don't know how half of our heavy elements are produced. It's as simple as that. And there's another process that I'll come to. It's called the P process that makes the proton-rich isotopes. This does not involve neutrons, but it involves gamma rays. Again, something neutral that it's not so easy to do, but it happens every once in a while. And then there's a whole a lot of, well, this picture that I'm showing you here has been around since the 1950s. 1959 was the first paper review article that explained all stellar nucleosynthesis and explained every single element we see around us. 59, that was a very long time ago. But it's one of those cases that the more you know about a field, the more you realize you don't know that much about it. So the more our telescopes improve, we now have observations that show that a lot of the stars cannot be explained by these processes or the stellar burning or anything at all. We need something else that we never even considered in the past. And now all of a sudden it's like, look at these observations, we can't explain them, we need something. Maybe there's a stellar environment that does something different that we don't know about. So it's a very active field. There's a lot of new things going on, especially in the last 10 years or so. There's a burst of activity, both from the observation side and from the nuclear physics side, exactly because of these new discoveries. So I'll come back to this problems later. Okay, so let me start with heavy element nucleosynthesis with the two neutron processes. S process here is the blue line, and R process is the pink line. And this chart here shows the abundances, same plot I had before, just isolating the two processes, the S and the R. Again, S is in blue and R is in red. So as you go through, you see that there are some peaks and some valleys in this distribution. And the first attempt was to try and explain where are those peaks coming from. So this is now why I spent the last hour explaining the basic nuclear physics that's going on, because we need it here. Let's go follow the pink line, the arc process. So it goes up. The way this works is neutron capture brings you to the right on this chart, and then beta decay brings you diagonally up. More neutron capture, more beta decay, and kind of just depending on who wins, you could do 3 neutron captures and 1 beta decay, or the other way around. So there's combinations of neutron captures and beta decays. And it keeps going like this until you see here, this is one of those magic numbers, and it goes 82. And see what it does? It doesn't go anywhere. It just stays right around the magic number, because the nucleus likes to have 82 neutrons. It doesn't want 83 and it doesn't want 81. But this is an astrophysical process, right? So as it flows through, the fact that it accumulates here, it stays on the magic number for a long time. This is what creates an abundance peak in our abundances. Now, if I follow the blue line, same thing is happening, same story, but it finds my magic number a little bit higher in mass because we're closer to stability, it's different nuclei. So it finds the magic number there. So then the peak in the S process is showing up a little bit higher in mass. So this is now the immediate connection why we, at least for some of us, why we study nuclear structure is because it has a direct connection with the observables we see in astrophysics. And trying to explain this means that we need to understand this. So if I go back to that evolution of magic numbers, if n equals 82 is not a magic number, not a good magic number out here, we haven't studied this nuclei, so we don't really know. This is a model. So if n equals 82 is not a good magic number here, and it's actually, I don't know, 90 that is a good magic number, then something else is going on that we'll have to explain this peak, or my arc process path might be going a little closer to stability, or a little further away from stability. These are all things that we don't know, and they all rely on the nuclear structure in order to define what is going on with the reaction flow. So this is kind of, again, one of my favorite pictures that shows that connection. Okay, so I'll go a little bit faster here. We don't need to stay into too much detail. This is the S process. So the way the S process works is that you would neutron capture. It's an environment with some neutrons, not too many, but it's enough to do some neutron captures. The rate of this capture is about a neutron capture every 1,000 years. So these are slow, but still they're there and they will do these neutron captures. And so if it's a stable isotope, can neutron capture and go over here, keeps going. But then if the final nucleus is unstable, see here it's 44 days, then this will just decay back. It doesn't have enough time to capture another neutron. And so the neutron, the S process just follows around stability. If the timeline, the half-life of the nucleus is similar to the timeline of the neutron capture, you can have a branching where it can go either way. And there must be percentages, you know, sometimes it goes this way, sometimes it goes this way, then it depends on the stellar environment and so on. But this is how you produce about half of the stable heavy elements. In terms of nuclear physics, what we need for the S process, I will say that the majority has been measured experimentally because it involves stable nuclei. So we've been studying stable nuclei for, I don't know, 70 years. And so the majority of these reactions has been studied, but there's a few that are still missing, especially on unstable isotopes, because these are hard to measure. And then there's the two reactions that kind of define what's going on. Is a reaction that produces the neutrons that are available to capture. And some of the reactions, this is the main one, but there's others that would be considered neutron poison. So they absorb neutrons out of the environment. So you need to know all of these reactions to know how many neutrons are out there and then how they capture on the available nuclei. So there's things called sensitivity studies where our theory friends will go into their model and they will say, okay, we're trying to figure out how much krypton-86 is produced in the S process. And so they'll go and they have all of these neutron capture reactions, so there's some beta decays and so on, and they'll vary them within their uncertainty up and down. And they say, okay, if I vary, I don't know, bromine 79 and gamma reaction, it looks like it does have an impact. But if I vary the 78 bromine and gamma, it doesn't do anything. So then they can provide a nice list for the experimentalists and say, okay, these are the reactions that matter, can you go and measure them? And so you need, within the field, you need to have the information. I can't just go and measure anything I want. It's just a waste of time. I need to work with my colleagues to identify through the sensitivity studies what is important, and then we go and measure that. And sometimes, you know, out of this whole list of reaction, maybe a handful I'll be able to measure because the other ones are hard experimentally, or the probabilities are small, whatever the problem is. So there's this is kind of the process. Okay, switching to the R process. This is a little movie that shows that R process flow that I showed you before. You can notice again the accumulation right at the magic numbers, and these, you know, as it goes up, this whole process takes about a second. And then once that whole thing ends, everything decays back to stability. So then whatever effects, nuclear structure effects you have out here, they will translate into the abundances that we see of the stable elements. So for the R process, this is quite critical because everything out here, you saw the limit of what we know and what we don't know. Everything out here where the R process takes place is not measured. We just did not have access to it experimentally. And with effort, we will have access to some of them, but again, not everything. So it's very important to benchmark our theory to be able to do to have good predictions. And of course, building new facilities like effort, it gives us access to nuclei we never had access to before. So in the R process has been all over the news for a while. Because of the gravitational wave discovery and the neutron star merger discovery 5 years ago. The community was kind of fighting, let's say, trying to figure out what is the site for the R process. People were saying supernova or neutron star mergers. But really, I think the majority there was a preference towards the supernova because neutron star mergers just take a very long time to evolve. You have to have one supernova to create one neutron star and then another neutron star in the vicinity, and then the two need to get together and merge. And so this takes a long time. And because we do see very old stars with our process signatures, people were like, well, it doesn't really make sense to have neutron star mergers. It's probably supernova. But the supernova had a different problem. There was no realistic way to have enough neutrons coming out of that supernova to have a full arc process. So both really had a problem. And so there was a debate in the whole community until 2017 when the observation of the neutron star merger happened. And there was a direct signature of an arc process happening in that supernova. And that was what is called the kilonova up there. So what's happening, there it is. So what's happening is that when the arc process takes place, then everything you produce decays back to stability. So all of those are radioactive decays. It's beta decay, they emit gamma rays, they emit everything they emit. So all of those gamma rays that are coming out of those radioactive decays, they don't propagate directly to us as an observable. They will go through the star, they change, they get absorbed, they get re-emitted, but all of that produces an electromagnetic signal that we could see on Earth. And it looked exactly as what was predicted. So there were two components. Again, I don't want to go into too much detail, but there were two components that matched exactly what was predicted. And these were the points of the observations, and it looks very, very similar. So it was, again, after, I don't know, the community, the nuclear astrophysics community, the only observables they had to compare to were the abundances either from distant stars or from the solar system. So things that came from an arc process that happened a few billion years ago, and we just see the result. And we go from that to seeing an arc process live in front of us. So this was a huge burst, a huge advantage for the community to try and figure this out. Okay. So again, nuclear physics, what is it that we need? We need the neutron captures on now exotic nuclei, and we need beta decays. These are so neutron rich that sometimes after they beta decay, they can also emit a neutron. And the environment is so hot that together with the neutron capture, we could also have the inverse reaction, the gamma N. So there's a lot going on. There's of course fission as well. When you make the heavy nuclei, they can fission back and feed this region again. So there's a lot going on. But again, this gives you an idea of what is the nuclear physics we need to study in order to understand this event. I put it all together here, what's known and what's unknown. So everything in color here are the isotopes where we know something about them. Doesn't mean we know everything, but we know something. And you see where the arc process takes place. We're barely touching the arc process with what we know right now. FRIP is that line. And so if you go to the lighter masses, we will be able to produce all of the arc process isotopes with FRIP. The heavier masses, not yet. But it's a huge improvement. It will have a big impact, or it's expected to have a big impact in terms of understanding them. Okay, so these are the two main processes that are going on. The rest that I'm going to talk about, they have contributions or smaller contributions, or they're brand new things that we've never seen before. One is the P process. Let me show you again. S process is here, R process out here, and then there's a couple of isolated isotopes that are on the proton-rich side that you can just not reach with the S or with the R process. The neutron captures always bring you to the right here. So those are the ones that are made by what is called the P process. Traditionally, it's called the P process because in that original paper that I talked about from the 50s, they thought that it was proton capture, but in reality, it's not. It's actually the reverse. It's gamma-induced reactions. It's in a supernova when the shock wave goes through a certain layer of the star that has the right temperature there. It excites nuclei, and then they start kicking out neutrons and protons. And as they do that, kicking out a neutron brings you to the left, kicking out a proton brings you down, kicking out an alpha particle goes diagonally. So this is how we can access those things. So there's 35 isotopes that require this kind of process, and that's again another active field of research trying to figure out how they're made, because we don't know the environment yet. Every model we have cannot reproduce what we see very well, so there might be contributions from other processes. This is really an open question. So I'll skip that. Nuclear physics. Well, it was kind of obvious. All of these gamma N, gamma P, gamma alpha reactions, or their reverse, this is what we need to understand the P process. There's a huge number of nuclei, and again, we have sensitivity studies, and there's, I don't know, 10, 20 reactions that seem to matter more. So this is how I identify our reactions. And then finally, I want to go to the new things. So I mentioned S, R, and P were introduced in the 50s, and we keep going. We still don't have all the answers. We keep trying to understand what's going on. But at the same time, there's new things that are popping up. So I'll show, actually, let's skip the new P process. I want to get to this one. Okay, so here's astronomical evidence that there's more things than what we think is out there, or what we can explain so far with the existing processes. I'll start with the top left. It's a single star. Here's the name of the star if you were ever curious to know what star was. And the black boxes are the observed abundances. And then the three different colors correspond. Red is the R process, blue is the S process. And then now yellow is a new process that I will introduce. But the point is that if you look at the S and the R, and you look at the heavier elements, a combination of those two can reproduce all the heavier elements. But if you go to the lighter elements, there are big differences, and you cannot really explain what you see just with the S and the R. You need something more. This was just a single star, and this has been around, I think, for a while, and people is like, okay, it's a single star, who knows? Maybe the astronomers didn't measure it right, who knows? It's a single star. But then in the meantime, we also got a whole group of stars. So every point on this plot is a single star. And now we have particular elements. Oh, it's cutting out here. This is barium over lanthanum, and this is lanthanum over europium. Astronomers like this double ratio things. But the point is that in this kind of plot where we have the different elements, the S process should show up in this box, and the R process should show up in this box. And really a combination of those two should show up somewhere in here. And there's a whole group of isotopes a whole group of stars that are doing something else. And it's not just one star, it's a very large number of stars that are doing something other than S and R. So again, there's reason, okay, we need to figure out what's going on with these stars. And then coming back to the meteorites and those stardust grains inside meteorites, there's grains where you see, this is now isotopic abundances. This is the big advantage I talked about. And every isotope, this is for isotopes of molybdenum. Every isotope, you know there's contributions from a different process. So these guys, for example, it can be produced by both S and R, the same as this guy. This is only S, this is only R, and so on. So this was a completely weird measurement, where they have two isotopes that are strongly enhanced. This is compared to solar system. They're strongly enhanced. But these are the only ones that are strongly enhanced. So if it was an enhanced S process, this should also be high. If it was an enhanced R process, then this should also be high. So it makes no sense that you have this kind of pattern. And again, this points to a different process. So these are all new observations in the astronomical community that point to that we're missing something and we need new processes. And so the I process came into play. I is for intermediate. So intermediate between S and R, intermediate in terms of timescales, intermediate in terms of how many neutrons you have. This is roughly the neutron density. The S process is supposed to be less than 10 to the 11, and the R process is supposed to be 10 to the 22. So this is right in between. I think I'll skip the way it works, but it's basically there's production of neutrons through one reaction. And it just happens that in an environment where there's a lot of mixing going on, you can have a replenishment of the seeds that you need for this reaction. You have more and more and more. That's why you end up with 10 to the 15. I can come back to it later if you're curious. Again, nuclear physics, the I process happens a few steps from stability. It's in between S and R. So we have access to all those nuclei experimentally. We know all of their properties, the half-lives, the masses, the binding energy, all of these things we know experimentally, except one thing, and that is the neutron capture. I'll come back tomorrow to neutron captures and why they're so hard to measure. But we know what we need and we can study it. There's that sensitivity study and the uncertainties we talked about. So if we have, let's say, a neutron density of 10 to the 13, we would actually expect to have this double ratio thing to be right where we want it. So this could work as an interpretation. The problem is that all these uncertainties coming from nuclear physics are very annoying, because this is, if you put in all the uncertainties from those neutron capture reactions, you end up with a pattern that is, let's say you cannot draw strong conclusions from it. So it could be that with the neutron capture rates, we're out here and we cannot explain a single star, or we're all the way out here, which is in between S and R, or we can actually explain all of this and we don't really know. Yeah.
Why are you working with this double ratio?
It's again, it's an astronomer thing, and I'm not an astronomer, but it just gives you kind of signatures, unique signatures in terms of the pattern of the different ratios. So europium, for example, is a good element. First of all, the selection of elements here are elements that they have good measurements of. They cannot do these measurements for every element in equally good ways. So these are, let's say, good elements. But then this ratio gives you an idea of the how metal poor is a star, or europium, I think, is the signature of the R process. So then compared to that, lanthanum to that gives you an idea of how far away you are from the R process. So they just choose elements where they know, oh, this is strong from this process and this is strong from that process. Okay, and I need to stop, so I'll just spend 1 minute on this, because this is the element production is not the only thing that the field of nuclear astrophysics is. So I want to at least give one example of a different thing. That's why I'm saying here, no contribution to abundances. So the RP process, it's the rapid proton capture process. It's a process that takes place in an accreting neutron star environment. So it's a neutron star with a companion star. It accretes material from that companion star. It's mostly hydrogen. And as that material accretes, once it gets to a certain limit in terms of mass, you can have an X-ray burst. And this whole process has nucleosynthesis, so it does have nuclear reactions that produce different elements. The problem is that those elements cannot escape the gravitational attraction of the neutron star, and they stay there. They become ashes for the next round of accumulating matter, and they go onto the neutron star, and there's new reactions happening, and there's a new generation of ashes, and it just keeps going like that. So X-ray bursts are the most frequent explosions that can be observed from astronomers. But still, all these observables, so instead of looking for abundances or meteorites and so on as your observable, you're looking at other things. You're looking, for example, at the light curve. And the different time evolution of those light curves will tell you something about the assumptions you made in your model, the nuclear physics that go in there, the conditions of the star, and so on. So this is just another example of what's going on, that we can have an observable that is not abundances. So again, we have all the nuclear physics. Here is mostly proton capture reactions. This is happening on the proton-rich side. There it is. And so once again, we need to know all the nuclear physics that goes in this in order to understand these events. Okay, so I think I'll stop here. I have a slide where I put all of the nuclear physics that we need. We need a lot, so we will be busy for a very long time. But this is something, again, trying to understand how our universe works, but in the lab, at the very basic level of the nuclear physics that goes into these processes, this is what's going on. I know I went a bit fast, so just stop me. I'm happy to discuss it, and I'm happy to come back to you tomorrow if you want to hear more about something. But my plan for tomorrow is kind of go through various processes or nuclear physics properties and dive more into how it is that we're measuring. And that's it. Thank you.